All right. All right. Welcome in everybody to another iteration of the Friday Lunch Seminar. I am super happy to be here and introduce Dr. Dang Pham. Dr. Dang Pham has joined the fam. You know, have you heard that one? Yeah, quite a bit. Dr. Dan, sorry. Oh, actually, I should have. This is Anne Marie is responsible for this bad joke. Oh. No, I'm just kidding. It was me. But Anne Marie was supposed to be here to give this introduction, but she may or may not be sick. We're not sure, so she decided to not come in. So after this is where Anne Marie comes in. The joke was all mine. So Dr. Dan Pham is the inaugural APS McCray Prize postdoctoral fellow here at CU Boulder. He defended his PhD in August at CETA, the University of Toronto, and he was working with Professor Hannah Ray, who, yeah, like Anne-Marie and I, correspond a lot because he's one of the main developers of Rebound, for example, which is the n-body simulator. Dang has worked on a multitude of topics, including photometric characterization of terrestrial exoplanets, a mapping instrument seeking to understand the epoch of reionization, and machine learning of protoplanetary disks. Today, he will be talking about his work on white dwarf pollution and comets. So, yeah.
All right.
Welcome to you, and thank you.
Yes, my name is Dang. I'm the new McCray fellow here. As mentioned, I just finished my PhD, and I'm very happy and excited to be here and see all of you. So today I will first talk about things I'm interested in, but can't fit into 40-30 minutes. And then I will talk about things I am interested in and can't fit into the next 30 minutes, 40 minutes. And as an eager 3-course meal, I will end with a sweet dessert, projects, things that I will just very quickly end on things I'm currently working on. So I'm broadly interested in dynamics and exoplanetary systems and in new ways to probe their properties and characteristics. I have worked on how to use an exomoon to tilt a planet's obliquity, and together with new measurements of planetary obliquity, can we use them to constrain the existence of an exomoon, for example. I have worked on developing new adaptive time-step criterion for n-body simulations to better resolve close encounters between bodies in the simulations. I have worked on, as Satya mentioned, characterization of terrestrial planets with statistical methods. And I have used unsupervised machine learning methods on planet formation simulations. If any of that sounds interesting to you, I'm happy to chat more. Oh, and also line intensity mapping. But if any of that sounds interesting, happy to chat more. But today I will be talking about these two papers here, one of which is the longest paper I've written, and the other one is the shortest paper I've written. So hopefully that should give some spice up for the talk. So the first I'll be talking about is about hoar clouds and white dwarf pollution. So about 25 to 50% of white dwarfs are unexpectedly seen with metal lines. Unexpected is because white dwarfs are very small. They're the size of the Earth, but they have about 0.6 solar mass, so they have very strong surface gravity. Because of that, the atmosphere is very thin, and the sinking timescale is very short. So any metals heavier than helium should not be there, but we do see them on up to 50% of white dwarfs. And this indicates that these stars must be constantly accreting materials from their surrounding planetary system. This is particularly exciting because now we can look at spectra of white dwarfs, and any metals that is heavier than helium, we know must have come from the surrounding planetary system. This gives us an unprecedented opportunity to use white dwarf spectra as cosmic spectrometers to understand the bulk composition of planetary bodies across the universe. So this was done here in this paper in 2021, where the authors compared the metal abundances on white dwarfs to the metal abundances on Earth and comet Halley. And as you can see, there's a wide variety of composition that they found, ranging from something that looks like a comet to something that's completely rocky, for example. And to reinforce this further, these two authors start to try to understand the kind of mantle rock types on bodies that were polluted white dwarfs. I'm no geologist, but I think this looks pretty cool. I don't know what these rocks mean, but I think this is really interesting to do. And this is difficult to do even in our own solar system. We had to send this space probe here to Comet 67P about a decade ago to understand the compositions of comets. And it's so hard that it costs 1.3 billion euros. I haven't checked the price of Keck observation lately, but I think it's cheaper to observe white dwarfs. Yeah.
How do you know that these heavy elements are created by accretion and not anything to do with nucleosynthesis on the surface of the white dwarf?
Yes, precisely because the sinking timescale is so short. So people have done simulations where to try to dredge up stuff from the bottom of the convection zone and to bring stuff from the surface up, but they all sink on like 10 to the minus 2 years. So it's very short sinking timescale. Oh, it also cannot come from the ISM either because the density of the ISM is not high enough to explain the accretion rate that we are seeing right here. So on the right-hand side, on the y-axis, this paper is showing the accretion rate on young white dwarfs. The x-axis, you can just think on the right axis are younger white dwarfs, the left, and going toward the left, the white dwarf is aging. And as you can see, the young white dwarf pollution rate is time dependent. But once you reach to become old white dwarfs, the accretion rate actually becomes constant. So this shows the accretion rate again on the y-axis. And on the left axis, as you go toward the right, the white dwarf becomes older. And as you can see, the accretion rate largely stays constant. In fact, the authors here constrain that the accretion rate does not decrease by more than an order of magnitude over 8 billion years. Now, this brings up a very interesting open questions right now in this field, which is, what are the reservoirs and mechanisms to deliver materials at such a relatively constant rate over billions of years in a very old planetary system? Remember, the sun takes 10 billion years to become a white dwarf. So by the time they become a white dwarf, this planetary system already has a lot of things going on. One source of pollutions have been proposed, which are small bodies, such as comets and asteroids. This is not a new idea. This was first proposed by Charles Alcock back from 1986, and there's been many proposals since, including my paper and Tatsuya, actually, from last year. So before I go on, I want to mention a few reservoirs of comets in the solar system. But it's important to remember that all of these are shaped by planet migration and planet dynamics. So first, we have the Jupiter family comets, which are at distances less than 10 AU. They are mostly dominated by the dynamics of Jupiter. And then we have the Kuiper Belt family comets, which is this distribution of comets here. Here, this is a simulation results of solar system comets from 2019, showing the distribution of eccentricity, inclination, and semi-major axis of comets in the solar system. This block right here, as I mentioned, is the Kuiper Belt. The 30 AU number is important because that's external to the orbit of Neptune, so it won't be kicked and scattered by Neptune multiple times. In addition, there's the scattered disk population of comets, which goes from 50 to 3,000 AU. Again, these things are formed by scattering of planetesimals in the early solar system as Neptune and Uranus migrates out. They have this curve of eccentricity increasing as semi-major axis increasing. That is because they are kicked by Neptune and Uranus, and Keplerian orbits are close, so they have to come back to where they were before, giving them high eccentricity. And the further you go out, you need for higher eccentricity to come back to where you were kicked. And finally, we have the Oort cloud. This population is completely different from the other ones. You can see that it's isotropic in inclination. They have all kinds of inclination. And thermalized. They have all kinds of eccentricity, going from 0 to 1. This is because out here, the gravitational effect of the galaxy now becomes important by something called the galactic tide. This distributes the objects evenly in phase-space, causing the eccentricity to be thermalized and inclination to be distributed evenly across the sky. They span from around 3,000 AU, which is the first distance when galactic tide becomes important, up to 100,000 AU. The 100,000 AU number is important because it is the edge of the sun's hemisphere. Beyond this distance, the gravity of the galaxy is more important, and you are very much more likely to be lost to the galaxy than bound to the sun. I will talk a bit more about the Oort cloud, since that is the topic of my first paper. As I mentioned, the Oort cloud is a byproduct of planet formation. And because of that, we expect most planetary systems with a planet to scatter things out and would be thermalized in the galactic tide. Therefore, most systems should have some sort of an Oort cloud. In the solar system, Oort cloud, it has a negative number density slope. All that means is there are more Oort clouds closer in than further out. It's characterized by this parameter gamma, and it's 3.5. We know that from simulations mostly. It can also be analytically derived if you are interested in that. The 7 major axis ranges from 3,000 to 100,000 AU, as I mentioned, and there are around 10 to 11 objects in the Oort cloud, making it a very populous population, with about 2 Earth mass in mass. So we're interested in studying how Oort clouds around white dwarf would behave. So we going to give a range of parameters for Oort clouds around white dwarfs between 2 and 4. And we scale down the outer edge because the white dwarf is less massive than the sun. So its gravitational effect is closer than it is than the sun. The number of objects and the number of cloud mass, we don't know that. But luckily, these numbers can be scaled very easily. So if you have a favorite number for that, you can just use my result and scale that up linearly. So for the first result, through simulations, we found that white dwarfs can indeed be polluted by solar system-like Oort clouds, and it matches the observed rates that we found. So here I'm overlaying my simulation results on top of the observational plot that I showed earlier. And as you can see, an isolated white dwarf, that is a white dwarf with only an exo-Oort cloud, can be induced to have pollution by Oort cloud objects at accretion rate from 10 to the 7 to 10 to the 8 gram per second, matching the majority of these dots. If you have a planet, this pollution rate is decreased by about 1 order of magnitude. And if you have a star, the pollution rate is decreased to below the current detection limit right down there.
The red dots are observations on the.
The red dot is for, I think, helium atmosphere, and the black dot's for hydrogen atmosphere. It all just to show this happens on all kinds of white dwarf. And more importantly, we found that the pollution rate can be sustained over 1 billion years. We tracked this through our simulations. On the left, you can see the pollution rate over 1 billion years in the existence of a 10 Jupiter mass planet. The accretion rate decreased by about a factor of 2 to 3, but no more than a factor of 10, which is again consistent with the observations. And if you don't have a planet, then the accretion rate actually stays constant over 1 billion years. To get this plot, we have to simulate a lot of comets to resolve the accretion over time. And to do this, we had to simulate about 10 to the 8 objects. And to do that, we have to develop a new simulation technique. Happy to chat more about that if that's something of interest. You can also scale this comet, planet, white dwarf system up to black hole test star if you want, and it's the same physics. So this simulation technique is applicable to many scales. And we will do this for 10 to the 8 objects over 1 billion years. Luckily, it only took 48 cores, so no supercomputer was involved, and only taking over 2 days. During the development of this, I actually broke my advisor's code, so I had to. That led to another paper on correcting the adaptive time step criterion in end-ball simulations that I mentioned earlier. And now I just want to say this is not particularly surprising, actually, that we expect Oort clouds to constantly hitting white dwarfs, because we do see Oort cloud objects in the solar system getting really close to the sun. In fact, this is from last year, 2024. There was a comet from around 30,000 AU reaching a pericenter distance of 0.3 AU. So it's not surprising to expect this process to continue after the main sequence also. And now my favorite, which is dynamics. I will now explain a little bit more on the dynamics of a white dwarf, a planet, and a comet, and galactic tide. So the main process to deliver something from tens of thousands of AU all the way to 1 solar radius, which is the tidal disruption radius of the white dwarf, involves mostly galactic tide. So galactic tide, you can just imagine the galaxy lives in the background, so it's this huge gravitational potential in the background. And because of that, it can induce something like a von Siepel Lidov-Kozai-like cycle, where it exchanges eccentricity and inclination to get. So this can bring things to really low pericenter by exciting to really, really high eccentricity. And if you're not an anesthist, and it looks like I just cast a spell there with that, all that means is this galaxy, the background potential is so strong that it's applying an angular momentum torque on the orbit and that caused the orbit to become very, very eccentric. This can be visualized by something called the loss cone. On the y-axis is the angular momentum, which also scales directly with the pericenter distance. So the goal is to bring things from high pericenter all the way to the gray zone here. This is the touchdown that we want. On the x-axis is just the semi-major axis. So toward the left, you are closer into the star. Toward the right, you are further out and you're closer to the galaxy. When you are closer to the star, your angular momentum torque by the galaxy is weaker, so you move slowly in. So you slowly diffuse through this angular momentum phase space. And once you reach one solar radius in pericenter, you get tidally disrupted, you make a debris disk, you pollute the white dwarf. On the other extreme, if the angular momentum torque is so strong that within one orbit, it actually can torque you all the way into the tidal disruption zone. So these are the two regimes of interest. If there are no planet or anything, this is the picture. The galactic tide will bring you all the way into the tidal disruption zone. Then the natural question is, well, we see a lot of planets in many planetary systems. In fact, we have observed a planet around a white dwarf and many other potential observations. So the question is, what if you have a planet? So this paper in 2023 by Chris O'Connor studied that process. And essentially, they put an additional. Sorry. All right, cool. All right, if you have a planet, that brings a problem because if your pericenter keeps crossing the orbit of the planet, then the planet can eject the comet, putting this barrier against pollution. So the only way to pollute the white dwarf now is if within one passage, you have to have such a strong torque that you directly get into the white dwarf within one passage. And that is the only way to pollute the white dwarf in the case of a planet, according to O'Connor. But unfortunately, we found that the process is actually slightly more complicated than that. The planet is actually not the worst thing ever. Because when you are external to the orbit of the planet, you can get weak diffusive kicks. That leads you to randomly walk in energy phase space, or equivalent in semi-major axis. Because you randomly walk in semi-major axis, you can actually also randomly walk to a higher semi-major axis, and then the galaxy can take the rest of you in. The only bad thing is the strong kicks. So when you have orbit crossings or orbit close to the orbit of the planet. Now, the natural question is how close is close enough? We studied this numerically. So on the right-hand side, I showed a scattering timescale. It's just a timescale on how many approaches that you would need to be ejected. And as you can see, when your pericenter distance is 3 times or more than the distance of the planet, then you are actually in the diffusive regime where you just have small semi-major axis kick, and you won't be ejected. Only when the pericenter is twice the orbital period, twice this orbital semi-major axis of the planet, only then you can start to get strong kicks, and strong kicks are the thing that eject you. This is the barrier, that is not the barrier. And the result of that is you can start to walk horizontally in energy phase space, and you can diffusively walk over here and having galactic tide pull you directly down. So moving vertically is caused by galactic tide, but now you can start to move horizontally. You are no longer trapped in where you were originally. And this is actually seen in the solar system simulations of comets. So in this paper from 2009, Uranus and Neptune kicks a comet diffusively so that it bypasses the barrier by Jupiter, and basically jumps down and are able to hit the sun. So this was seen in the solar system. In our paper, we just show that you don't need multiple planets to do this. Even one planet can diffusively walk you inward. I mentioned the scattering barrier. So that's the energy barrier on top of the phase space. But having a companion, you can treat the companion as a wing. And that gravitational wing can also induce a torque. And that torque, if it's strong enough, can overcome the torque by the galactic tide itself. So this is called an angular momentum barrier. And we analytically estimate the the effect of this angular momentum barrier by comparing the precession rate caused by galactic tide divided by the precession rate caused by this planetary ring. It turns out that it comes out to a pretty nice expression where the first term alpha just compared the density of the galaxy to this density of this gravitational ring. And the second term just compares the geometry of the orbit of the comet to the geometry of the orbit of the planet. And here, if zeta is greater than 10, you are dominated by galactic tide. So if zeta is greater than 1, then galactic tide is able to bring comets in and do the whole thing that I just mentioned. But if zeta is less than 1, then this ring actually overcome galactic tidal force and is able to out-torque the galactic tide, also preventing pollution. We tested this numerically. On the right, I showed, well, basically the same thing, just from numerical simulations. And as you can see, the contours of zeta match very well. So I've mentioned two things, this energy barrier and this angular momentum barrier. Now the question is, when are they important? And they're important depending on the companion. So if you have a planetary companion, it is not big enough to cause this angular momentum barrier. A planet would never have enough angular momentum to overcome the angular momentum of galactic tide. But a stellar companion, starting from an M dwarf and go above, has enough torque to prevent galactic tide to be effective. We also calculate the distance where the scattering is important, and you can put that all together into this really complicated slide. But all that matters is if you have a stellar companion, it is very hard to pollute a white dwarf, simply because the angular momentum is now being out-torqued. But there's another very simple reason why it's really low for a stellar companion. And the one reason is that you have two binary bodies. The center of mass is not within the body itself. So this comet is now orbiting that center of mass exterior to the two bodies. So now you have to calculate the rate at which a test particle would impact either of these bodies. Hopefully one of them is your white dwarf. So this can be done by something called the Safronov number. And all you need to know is if the Safronov number is less than 1, collision is likely. And when you calculate the Safronov number for this, it comes out to be 2 times 10 to the 3. So it's also very unlikely to collide randomly to either of these objects. All right. I hope that was enough interesting dynamics, and I will talk about something completely different now. Hopefully that's not too much whiplash. Now we'll talk about fast radio bursts and interstellar objects. On the same theme of small bodies and small stars, interstellar objects are small, neutron stars are also small. Yes.
Fascinating question. I can't possibly explain. Which one was the longest paper and which was the shortest paper?
Which was, sorry, what?
Which was the longest paper and which was the shortest paper?
The Oort cloud paper is the longest paper. So now we're for the reprieve. It's almost done. No, it's all good. It's all good. It's all good. It's all good. No, I'm just joking. So for some context, fast radio bursts are radio events, as you might imagine from the name. They are very fast. They are on a millisecond time scale. The first fast radio burst event was discovered in 2007, and this just shows that event. It spans many frequencies. It sweeps through frequency space, and it lasts in the order of milliseconds. There are many debated origins on the mechanisms. On the origins and mechanisms of fast radio bursts, most of which involve some sort of neutron stars. One proposed radiation mechanism is through the collisions between planetesimals, like comets and asteroids, and neutron stars. This was originally proposed to explain GRBs, gamma ray bursts, but unfortunately the energetics doesn't work out for that case because a GRB requires something on the order of 10 to the 51 Earth. Fortunately, fast radio bursts are more on the order of 10 to the 36 Earth. So from the purely energetic point of view, this potentially should work out. One source of small bodies in the universe, outside of Oort clouds and Kuiper belt and scattered disks, are interstellar objects. In fact, there are 10 to the 15 interstellar objects per parsec cubed in the solar neighborhood, which is a huge number. And this was constrained from Oumuamua. So they had a volume limited surveys, and they have one event, so you can use Poisson statistics to infer that. It's kind of sketchy, but now we have 3i Atlas, so this new thing, so hopefully this number should be revised a little bit. I was talking to some of them and they said, oh, it should be like 10 to the 14, no big deal. So it's on the order of the same. So we have numbers from 2 measurements. But if you take this number, and you can also do this number from a more forward modeling point of view, about 99% of things in the solar system are ejected. So planetary systems are very efficient at ejecting things out. The Oort cloud originally had 10 to the 12 objects. You take that times 100 because 99% efficiency, you get 10 to the 14 as an object per second. So it's somewhat feasible. And we found that the number of neutron stars and interstellar object collisions are consistent with the cosmic FRB rates. And this was just done by using the number density there and the number density and the star formation of neutron stars. And we just infer that across the universe. In addition, we found that the FRB time duration correlate to the expected planetesimal sizes that we know in the solar system. On the x-axis, I show the post duration of an FRB event from the first CHIME catalog, which is just a Canadian fast radio burst experiment. And you can see that this corresponds to the planetesimal sizes between 500 meters to 10 kilometer. There's somewhat of a cutoff here. This is not real. It's due to hardware limitation. CHIME has the time temporal limit of 1 millisecond, which is right there. So hopefully with new instruments, this should keep going up. I also plot the sizes of the previous 2 interstellar objects we were found. 3i Atlas is still being revised, but I think it's somewhere on the order of 1 kilometer, so it's not too different. In addition, this can also explain subburst. So FRB events, most of them have single bursts, and then last number have 2 bursts, and then triple bursts are even more rare. And this corresponds to the binary and tertiary asteroid population in the solar system. So there's a purely phenomenological prediction here that if this is true, then single burst should be the most common, and then binary bursts following from that. And pushing it even further, bigger objects crashing into a neutron star create bigger event. So we can correlate the energy distribution of FRB and the size distribution of planetesimals that we know in the solar system. So on the top, I show the equivalent energy distribution for typical planetesimal sizes estimated in the solar system. And on the bottom, I show the observed FRB power law distribution. And as you can see, it's within the error bar, albeit the error bar is huge. So maybe if they get better measurements and we find that, this would also be a falsifiable aspect.
Do you know the distance to these things?
Yeah, so some you can estimate the distance, do a lot of dispersion measure kind of physics and math and stuff like that. It's really hard to localize them. That's the issue. That's the biggest issue of getting the distances. Because they have these like huge array. So the most thing is like
it's a big FRB versus a small FRB.
Yeah,
you know the distance well enough to distinguish that.
Yeah, so the best actually is from the Milky Way. We have one event from the Milky Way. So that's one way to estimate the distribution there also. But yeah, no, it's a very small. That's why the error bar is so big. I think it's only a handful that they can actually localize. There are some other implications of this. One is that there are more neutron stars as the universe ages. There are also more planetesimals as the universe ages. So in this hypothesis, the FRB rate should increase over cosmic time. The other implication is that of the host galaxy morphology. When a neutron star is born, it gets a really strong kick on the order of 250 kilometers per second. And that essentially can be ejected from the disk of the galaxy. So in a disk galaxy, when these neutron stars are kicked out of the disk, they cannot create FRB events anymore because there are no interstellar objects in the outside of the disk because there's no planet formation. So one prediction of this is elliptical galaxies should have more FRB events than, say, a disk galaxy. All right, now I'll just end quickly. I think I'm almost at 30 minutes yet. I will just end with some current projects that I'm currently working on. this hopefully should be sweet and short. The first thing I'm working on are the volatile content of comets. This is inspired by the fact that most observations of polluted white dwarfs do not see comets-like composition. So one potential explanation of that is, well, most planetary systems are rocky, potentially, or the other implication, but it's also the fact that the sun will become 5,000 times more luminous in the post-main sequence evolution. So a natural thing to ask is what happened to the volatile content of comets after the main sequence evolution. But it turned out to be quite a tricky project because we have to couple stellar evolution to dynamical evolution, to thermal evolution and chemical evolution. And these have very vastly different time steps. Like on a comet, the time scale for amorphous ice to change to crystalline ice is like very fast. But if you have a pericenter passage close to the star, because you have an eccentric comet, that could even be faster, right? Then you have the thermal time scale, which ranges many orders of magnitude itself. I spent a year just developing this new code. Hopefully it's almost done. And we use it to trace the volatile contents on comets during the post-main sequence stage, with the goal of trying to explain the distribution of volatile contents on polluted white dwarfs. My second project is you have these materials that come close to the star. It becomes a debris disk, as I mentioned. These things could be ionized. And if your white dwarf is magnetic, which some of them are, then your ionized material would follow the magnetic field line onto the white dwarf. So the natural question is how big would the spot of material be? And the other question is, okay, you got it to the atmosphere of the white dwarf. How long is that sinking timescale, and can they spread over that sinking timescale? And this is to explain some recent observation of photometric variability on magnetic white dwarfs. It could also have implications on the accretion rate, because now everything is being accreted to the small spot. But when we observe a star, it's averaged over the entire star. So then what's the difference in the accretion rate there? And now this is my conclusion slide. I'm interested in many things, happy to talk about anything, and happy to be here.
Any questions for Danny?
That was such an interesting talk. I'm so excited to have you here.
Thank you.
It's super impressive. I am sorry, part of my ignorance. How hard is it to measure the FRP rate in like spirals versus ellipticals? Is that like a hard measurement?
It's mostly just because they can't really localize which galaxy it came from. They just know it's like some like 30 arc-minute range. You're like, yeah. But I think there are some new telescopes coming up, and they have better localization. So I'm pretty excited for that. There are also something called scintillometry, and they were able to constrain that most of these fast radio bursts came from some sort of event close to the neutron star. So there's also a class of events that cause like greater distances than impact to neutron stars. So that's been ruled out. So it's got to be something with neutron stars.
Again, this is awesome. Can I ask a little bit, maybe for both of these projects, the last little bit here between objects plunging in on a very different orbit. Here is it boom, it falls onto the white dwarf where you don't start directly, or is it tightly disrupted right beforehand of the spread? Like, what does that look like?
So for the white dwarf, it becomes a disk, and that disk feeds in on the Poynting-Robertson just timescale and process. For a neutron star, it's actually a radial event, because it's just a neutron star flying through this field of planetesimal, and these things are getting gravitationally focused onto the neutron star. It's not just the cross section, because the cross section of the neutron star is very small. You will never collide anything with that. But because it's not just such a strong gravitational focusing, these things have radial orbits onto the neutron stars. So for the neutron star, it's directly onto it. And that's why it causes these events to be so short. That's why it's milliseconds kind of event. That's how long it takes to disintegrate the whole thing, crash into the neutron star. Yep.
Kind of a silly question, but which is your favorite paper? The long one or the short? Cause I have personal feelings about links to papers that I published in, so.
The long one was fun to work on. It got long because my advisory committee keep asking, what if there's a whiteboard binary? And you're like, okay, I'll do that. That's important. It's dragging on, but I like it because it's actually a complete, like every single thing was explored. The smaller one is kind of a fun paper. It's just like, oh, what if this is a thing? And potentially can you falsify it with observation? So it's different in that sense. I think I like the longer one actually.
Okay. Yeah, for the events where there's two radio bursts, is the delay between them consistent with what we would expect for binaries and pollen?
Yes, it's a slightly more tricky calculation, but in short, yes, we check that. It's the spread is sub-millisecond, and the separation between binary asteroids are not far either, so it's somewhat consistent. Yeah, the best answer to the second project would be you should run an MHD simulation, and actually model the tensile strength of bodies and yada yada. But that would not be a short paper.
Any other questions for Dan? If not, I might ask him one more. That's more of a real question. So you mentioned I'm actually a little bit interested in the tracing the volatile elements, the code that you mentioned at the very end.
Yep.
Maybe it's just less of a question, but I just wanted to learn a little bit more about what I'm working on right now.
So because there's so many timescales involved, we wanted to integrate over such a long time, we had to integrate over the post-speed sequence timescale, which is 400 million years. That's the longest timescale involved. The shortest timescale involved is the crystallization rate of ice, which is only order of seconds. So we have to do something called an adaptive time step.
Yeah.
To it again, as you might have heard by now. But essentially, it's we constantly have to change the adaptive time step to the shortest time step available at the physics at that point, and then tracking that. And luckily, most of the time, the shortest time step is actually the dynamical time scale. It's the shortest time scale. It's the pericenter time scale approaching the star. That dictates how hot it is because you're close to the star.
Yeah.
And because how hot it is also affects how fast the ice crystallizes. So that it all works together at the end, and it uses that new time step criteria that I developed. So it's kind of a nice tie in that sense.
And how much does it slow things down compared to like just a good old rebound simulation? With
a lot, because you have to solve PDE, right? You have to solve the heat equation. You have to solve the equations for the volatiles to evaporate. You have to solve the equation for the ice to evaporate, the water ice to evaporate crystallizes. So it becomes from, like F equals GMM equal R squared all the way to like 59 coupled ODEs, unfortunately.
Yeah.
It's also a grid, right? Because you have to like make cells, and it becomes really complicated. So that's why it became really hard. I did an order of magnitude estimate of it first, and just some silly numbers come out. So you actually have to do a true simulation.
That makes sense. But yeah, like I'm excited to talk about that later.
Yeah.
So,
And I think Anne Marie has a question online. So does Greece. Maybe we'll go to Greece first.
Am I audible?
Can she go first?
Yes, I think I can hear you.
Okay, yeah, thanks a million. I'm sorry I'm not able to be there in person. I've had a COVID exposure, so I didn't want to sit amongst everybody coughing weirdly on purpose. I was interested in what is your ideas on what happens to half of the material when a comet gets tidally disrupted. So in a typical like stellar tidal disruption, it's pretty standard. We think about half the material remains bound to a black hole and half the material flies outward. So the same thing should be happening with a comet and a white dwarf. It seems like if we're explaining a lot of the white dwarf pollution with this model, there should be a lot of cometary debris just scattered at a high velocity.
Yes, 100%.
Away from,
Left around after this process. Luckily, the accretion rate observed on white dwarfs ranges like 4 orders of magnitude. So losing half of it is not really a big problem for the observation point of view.
But would you expect like maybe to see evidence of this from like dust flying outwards from white dwarf systems? Like, is there anything else that you could predict?
Yeah, I think people have written papers on like debris disk and like dusty white dwarfs from the SED. I'm not too familiar with what sort of other observational implications it would be. It might be interesting to think about.
Yeah, the motivation for the question actually is a paper where they were looking at asteroids being tidally disrupted by white dwarfs, and the material that gets stripped and ejected could form things like Oumuamua, these like strangely elongated shards.
Right.
So yeah, it's just kind of
I
something.
think that's certainly possible, and the fact that Oumuamua is much smaller than a typical comet would also. Yeah, I think that's a very interesting idea.
Be like a unifying theme between your two projects as well. Then the interstellar asteroids coming from white dwarf systems smash into neutron stars.
Yes, for sure.
Yeah, thanks.
Okay, let's go to Garish. Do you have a question?
Yes. So you talked about the delivery being from the leftover debris disk after it's been disrupted, falling onto the surface via Poynting-Robertson drag. But I haven't seen an actual start to finish simulation that includes that step. And it seems like a thing that's doable with rebound. Have I just not seen it? Or
I think it's a paper from 2011 by Roman Rafikov, and he analytically calculated that rate. So I think people just take it at face value there. He found that the rate is about 10 to the 8 gram per second, matching the observed rate. And I think that is the consensus of the field right now. I don't think people have bothered to just because of that.
Okay. And then relatedly, once upon a time, I tried to get Rebound to work on rubble pile asteroids.
Yes.
It was very, very hard. Is it any easier now?
Yes, I think so. I think with my new simulation thing, if you treat your rubble pile asteroid as point masses, then I think it should run pretty fast now. If the concern was running time, I'm not sure what issues that you had.
So the problem was if I wanted to model the rubble pile properly and account for collisions between point masses of the rubble pile, right? Your dynamic time step goes to how long does it take for things next to each other to bump into each other, and that becomes hard.
I know that Hano is working right now on the fragmentation and whatnot, so maybe this is coming up soon. You might want to contact Hano if that's something of interest, because I know it's something that he's working on right now, fragmentation and collisions and whatnot.
Great, thanks.
Yep.
Okay, any final questions in the room? All right, let's thank Dang again. So Dang still has some slots in his schedule if you want to sign up to meet. Otherwise, he'll be around, and thank you all for coming.
Thank you.
Thank you.